Welcome to our channel. Today, we discuss a topic that is as fascinating as it is critical: why Mars cities may face a severe oxygen crisis by 2035. Imagine, for a moment, that humanity has finally established permanent settlements on the red planet. Colonies rise from the dusty Martian plains, greenhouses flourish under artificial lights, and humans walk across the alien landscape in pressurized suits. It sounds like the stuff of science fiction, yet we are rapidly moving toward this reality. SpaceX, NASA, and other organizations are pouring billions into Mars colonization, aiming to make humans multiplanetary. But as thrilling as this prospect is, there's a looming danger that doesn't always make the headlines: a potential oxygen crisis. Now, oxygen might seem like a simple resource. After all, it's just a gas we breathe every day here on Earth. But Mars is profoundly different. Its atmosphere is 95% carbon dioxide and only about 0.13% oxygen, which is essentially negligible for sustaining human life. To put that in perspective, Earth's atmosphere contains roughly 21% oxygen. That small difference is massive. It means Mars is practically inhospitable without sophisticated life support systems. For any city on Mars, the availability of breathable oxygen isn't just a convenience, it's the difference between life and death. So why do experts think an oxygen crisis could hit by 2035? Well, there are multiple factors at play, starting with the limitations of production. Current Mars colonization plans rely heavily on technology like MOXIE, the Mars Oxygen In Situ Resource Utilization experiment installed on the Perseverance rover. MOXIE converts carbon dioxide from the thin Martian air into oxygen. It's a brilliant piece of engineering, but there's a catch. Right now, MOXIE produces about 10 grams of oxygen per hour. That's enough for a small fraction of a human's daily needs. Scaling this up to support a growing Martian city of hundreds or thousands of people is a colossal challenge. It's not just about building bigger machines, it's about the energy, materials, and maintenance required to keep them running in Mars' harsh conditions. Energy is a huge factor here. Solar panels are likely to be the primary energy source for early Martian colonies, but Mars receives less sunlight than Earth, about 43% as much on average. Dust storms, which can last weeks and cover the entire planet, can reduce solar power generation to near zero for extended periods. Without reliable energy, oxygen production would be jeopardized, leaving cities at risk of depletion. Imagine waking up in a Martian city and realizing the oxygen levels are dropping because a massive dust storm has prevented your solar arrays from functioning. The stakes are high, and the consequences are immediate. Another critical concern is storage and distribution. Oxygen isn't just produced, it has to be safely stored and delivered to habitats. Transporting large amounts of liquid oxygen is extremely risky because it's highly reactive and must be kept at cryogenic temperatures. Pipelines, storage tanks, and pressurized systems on Mars would need to be exceptionally robust. A single failure could have catastrophic consequences. Unlike Earth, there's no atmosphere to buffer mistakes or provide emergency resources. An oxygen leak in a Martian city could mean instant danger for its residents. Then there's the biological demand for oxygen. Early Mars colonies will likely use plants and algae to supplement oxygen production, both for air quality and as part of food systems. Photosynthetic organisms can produce oxygen, but they require precise light conditions, water, and nutrients. Mars isn't exactly hospitable for these needs. Water is scarce, light levels vary, and the soil is toxic to Earth plants without significant processing. Scaling up bioregenerative life support systems is feasible but resource-intensive and highly sensitive to failure. A malfunctioning greenhouse could reduce oxygen levels faster than engineers can compensate, especially if multiple systems rely on interconnected loops. Population growth compounds the problem. Initial colonies might start with a few dozen people, but by 2035, some projections suggest hundreds or even thousands of settlers could inhabit Mars. Each additional person significantly increases oxygen demand, as well as the need for food, water, and waste recycling. If oxygen production doesn't scale at the same pace, shortages will occur. Unlike on Earth, Mars cities won't have the luxury of importing massive oxygen supplies from elsewhere. Every molecule has to be produced locally, with extremely high efficiency. Psychological factors also play a hidden but vital role. Humans are not only biological consumers of oxygen, they are also susceptible to stress, anxiety, and panic. Living under the constant threat of an oxygen shortage could create a tense, high-stakes environment, impairing decision-making and increasing the likelihood of errors. A Mars city could face cascading crises, a technical failure leading to low oxygen, stress-induced mistakes by colonists, and a potentially deadly outcome. Unlike Earth, there's no immediate rescue option, so contingency planning must be flawless. Then, we need to consider the environmental hazards unique to Mars. Cosmic radiation, extreme cold, and dust storms aren't just threats to human health, they also impact oxygen systems. For instance, dust can clog machinery, solar panels, and life support intakes. Radiation can degrade materials over time, weakening storage tanks and pipelines. Even small, gradual damage could accumulate into a system failure if not meticulously maintained. On Earth, we take atmospheric oxygen for granted, but on Mars, it's a fragile, highly engineered lifeline. There's also the question of efficiency. Producing oxygen from carbon dioxide requires energy-intensive processes like electrolysis or chemical conversion. Current estimates suggest that for a single person, maintaining breathable oxygen continuously requires a massive amount of energy and materials. Multiply that by a population of hundreds, and the energy requirements are staggering. Unless colonies can develop breakthroughs in energy generation, perhaps nuclear reactors or highly efficient solar systems, the oxygen supply may struggle to keep pace with human demand. Beyond production and storage, logistical challenges are daunting. Consider maintenance schedules, spare parts, and redundancy. Mars is millions of kilometers away from Earth. If a critical oxygen production module fails, replacing it won't be as simple as ordering a part from Amazon. Manufacturing spare parts on Mars is possible but limited by resources and technology. Colonies would need multiple backup systems and contingencies for every scenario. Even small miscalculations could have dramatic consequences. Let's not forget the ethical and social dimensions. If oxygen becomes scarce, how will a Martian society decide who gets priority? Will it be first come, first served? Will there be rationing? How will conflicts over life-sustaining resources be resolved? These are not theoretical questions, they are very real issues that early Martian cities may face. Preparing for an oxygen crisis is not just an engineering problem, it's also a governance problem, requiring careful planning and social cooperation. Interestingly, researchers are already investigating alternative solutions, like importing ice from Martian poles to produce oxygen or using regolith-based chemical extraction. However, these approaches are complex, slow, and resource-intensive. They could supplement oxygen supply, but they are unlikely to fully solve the problem for large populations. Mars may be abundant in raw materials, but converting them into usable oxygen is an engineering nightmare that requires foresight and meticulous planning. Another consideration is long-term sustainability. Early colonies may survive with heroic effort, but sustaining life for decades or centuries demands self-sufficiency. Oxygen systems must be resilient, redundant, and adaptable to changing conditions. Any failure could jeopardize not just a single habitat, but entire settlements. In other words, the risk of an oxygen crisis isn't just immediate, it's systemic, affecting the entire foundation of human life on Mars. So what does all of this mean for the future of Mars colonization? In short, it means we must be realistic. Establishing cities on Mars is a monumental achievement, but it is not without profound risks. Oxygen, something so basic that we take it for granted on Earth, could become the limiting factor for human expansion into space. Without breakthrough technologies, innovative designs, and careful planning, we could see early Martian settlements struggling to survive under the weight of an oxygen crisis. However, there is hope. Engineers and scientists are actively exploring ways to scale oxygen production, improve energy efficiency, and develop resilient life support systems. With the right investments and foresight, it is possible to avoid this crisis. But ignoring the problem or assuming that Earth-based systems can be transplanted directly to Mars would be a grave mistake. Humanity's success on the Red Planet depends not just on ambition, but on deep technical understanding, robust systems, and social preparedness. As we look toward 2035, it's clear that the oxygen question is a test of our ingenuity and responsibility. Will we rise to the challenge and create sustainable Martian cities, or will we confront a harsh reality that even advanced technology cannot easily overcome? The answer depends on the choices we make today in planning, research, and innovation. So, if you found this discussion eye-opening, here's what you can do. Make sure to like this video, subscribe to our channel for more fascinating discussions about space, science, and humanity's future, and leave a comment below sharing your thoughts. Do you think humans will overcome the oxygen challenge on Mars, or are we rushing into a crisis we may not be able to manage? We'd love to hear your ideas. Thank you for watching, and we'll see you in the next video where we continue to explore the mysteries and challenges of space exploration.